I'm happy to be here. I'm quite new to the Swiss map collaborations, but I'm very glad to meet you all for the first time. I started 1st of March, so I didn't have quite much of possibilities to interact with people outside my group, but this is a very nice opportunity. Let me say that I'm sorry for this very general and broad title to my talk, but it's somehow the title of a project which is very close to my heart, and is a very long-term project that I have with people at Heidelberg University, which was my place where I had my postdoc before coming here, before joining ETH. And the project is in the framework of this collaboration, and I want to just say a few words about this collaboration because I believe it's somehow, it's probably a bit bigger than SwissMap, but it's a similar scopes. It's a collaboration between physicists and mathematicians, and also computer scientists, by the way. The speaker, one of the speakers is Manfred Salmofer, that probably many of you know, and so I'm also a member of this collaboration and this project, and I'm going to talk to you about, or at least I'm going to talk to you about some early results of this project has been financed within this structured collaboration. So we have somebody, a postdoc that's working in Heidelberg, and many people are collaborating with me, and I am an external member of this collaboration. So I hope if you are interested to collaborate with us or with any member of the structured collaboration, you can find the website online, and I am also a member there, and I would be happy to keep people in connection, make invitations, and so I think it will be very fruitful because there are common scope and common methodologies. Okay, now I have done my token of advertisement, and so now maybe this justifies also my general title, because in this collaboration there are many people. But actually the project is very much focused on statistical physics and on phase transition, which has been my interest since my PhD. So, well, I guess phase transition is a very general topic, very broad. Probably everybody has had a course or two courses during his studies on phase transition and on universality. So close to a phase transition, we know that thermodynamic quantities exhibit scaling behavior, and the scaling behavior, it's independent on the microscopic details of the model at hand. So for example, here we're showing the density and the temperature of a lot of different gases close to the critical point with the liquid vapor transition. And you see that this, when plotting this way, all the curve collapse in the vicinity of the critical point. Also, dynamical systems have issues of universality. I don't think I need to spend a lot of time in it. For example, there's been plots of earthquake, the number of earthquakes over the year with a fixed magnitude, and you should see that it displays scaling laws. So it's a bit difficult to give a rigorous mathematical definition of universality, and I think it doesn't exist, or at least I couldn't find it out. But there is somehow, from a very physics perspective, there is an operative definition that phase transitions are normally characterized by order parameters, and the order parameters depend close to the critical point from a control parameter that now I call epsilon. And probably there will be some mismatch of notation, and I will let you aware of. But in this case, I'm just calling epsilon the control parameter of my phase transition in such a way that when I am exactly at the phase transition, epsilon is 0. Here I'm specifically talking about second order phase transition, because universality is something related with second order phase transitions. And so when you have an order parameter, and this order parameter displays a certain symmetry, and during my talk I will be mostly talking of vector symmetry, so order parameters which are vectors, so which are symmetric under rotation in some ON space. And once you fix the dimension, and that's the key point of my talk. So I'm trying to give you some operative or wavy definition of universality, or sorry. So basically my point being, there is no rigorous definition of universality, but when I have a second order phase transition with an order parameter, and the order parameter display a certain symmetry, and I define the dimension on the system, and the dimension of the system enters in the calculation of the density of the density of modes now. Sorry. So basically entering the low energy density of states for the phase transition, you can define a quantity that's universal. For example, this beta would be universal normally at second order phase transition when it only depends on the symmetry of the order parameter and on the dimension of the system. And what I mean for the dimension of the system, on the low energy behavior of the density of states. So this is what I would say it's a definition of universality. So quantities close to a second order phase transition which only depend on the order, on the symmetry of the order parameter and the low energy tail of the density of states. But if they only depend on the low energy tail of the density of states, it means that whatever is my microscopic statistical mechanic model, I can build up a continuous model, and this continuous field theory model, if you wish, has the same universal properties. And this is also acts as a definition of universality. So you can define a quantity universal if you can remove all the lattice feature of your statistical mechanics model and still get the same number for this quantity. Okay, so I love simple models, maybe in contrast with many people, but I love very simple models. So for example, I can consider a standard phi to the 4 theory. It's just the continuous version of the Ising model, or at least it's in the same universality class of the Ising model, in the sense that it has a phase transition between an ordered and a disordered state. And this phase transition is characterized by critical exponents. I will use only 2 because I know that only 2 are independent of each other, and all the others I can obtain from these 2. And I like the definition of critical exponents that comes from renormalization group. And so these 2 critical exponents are the correlation length, which appears in the correlation functions a little bit off of the critical point, and the eta, which is called the anomalous dimension, which controls the power law decay of the 2-point correlation function exactly at the critical point. So the interesting point is that for the Ising model, or for the phi to the 4 theory, once again, it's the same universality class, so universal properties are the same. These 2 numbers have been computed in very different ways. So you can start with the dimensional regularization approach by Wilson, which is very old. It comes from the 70s, from the first definition of renormalization group. But it has also been computed very recently and supposedly exact with conformal bootstrap technique. And also there is my, let's say, my token of contribution, because we also computed it with functional renormalization group. And the nice thing of all these approaches is basically the dimension is just a parameter. So in the continuous theory, there is no reason not to use a dimension which is not an integer. On a lattice model, it's a bit tricky to do it. But when you study a field theory, and the field theory as it is here is translational invariant, D can be any real number. And indeed, we can do the computation by analytic continuation in dimensional regularization or in FRG, or in Bootstrap, it's just a number. So it's an input of your numerical calculation, and you can compute these critical exponents as a function of the dimension as if it is a real parameter. Okay, so now the problem is we have this number, and you see, okay, we cannot solve exactly these theories. So these numbers contain some degree of approximation, apart the bootstrap that it's supposed to be exact, but there is no proof, mathematical proof that it's exact. Just we know that it agrees to all digits with best Monte Carlo estimates, so with best numerical simulation. So these numbers are all kind of in agreement with each other. So the concept of a real dimension, of continuous dimension, is operatively, I would say well-defined. And if somebody has something against it, we can discuss it.
Is your point that there is an analytical result from the bootstrap for the critical?
No, it's not analytical, that's the point. It's numerical, but it's supposed to be exact in the sense that their numerics gives a lot of digits, and all the digits correspond exactly with the Monte Carlo simulation. This is why I called... Oh, well, in the sense Monte Carlo, we can discuss about it. I think it's a bit of philosophy. I don't want to... I'm just saying Monte Carlo, it's a simulation. While conformal bootstrap, maybe you got some insight because you are solving some operator product expansion. It's a more theoretical method, but okay. Monte Carlo is a little bit in between theory and experiment. You know, it's an experiment you do on the computer. The bootstrap, it's in a formalism, which is theory, but it's still numerics. So I don't want to... I am not even of that side of the church. So if we want to say that it's not exact, I'm happy. Perfect. Huh? So now the question is, what's the meaning of this non-integer dimension? So we see that we got a picture on that side, and but we don't know what is. So when I have a real model in reality, I don't have a continuous model. So normally in reality, there is some lattice, or if you also we are talking about quantum gases, there is some ultraviolet cutoff that can be the range of your interaction or whatever you want. So are these results in a real dimension? Can they be applied to actual lattice models? So in my opinion, the answer should be yes. And it should be that you should just find a lattice model which has the low energy tail of the density of states, which behave as a power law. And this power law allows you to define what we call a spectral dimension. And the spectral dimension, which is, so you see, you take the vibrational spectrum of a lattice model, or for example, you can take the return rates of random walk. We know that random walks are just basically completely determined by the spectrum of the model. So somehow, if you take these two quantities, ought to be the same in some sense. There are various definitions that you can give of the spectral dimension, but this spectral dimension should be the correct definition of dimension for structures, for complex graph, which have no translational invariance, but still a power law decay of the density of states of low energy. Okay, so now my point is, we are not sure, or maybe I am sure, but not everybody is sure, that universal properties as a function of the continuous dimension in the renormalization group or in the field theories approach in general are realized on lattice, or sorry, on graphs, on non-homogeneous graphs, where the spectral dimension coincide with that number. But we know some mathematically exact results. The mathematically exact results are that if you consider the Mermin-Wagner theorem, which is the theorem, the mathematical theorem that forbids continuous symmetry, so XY, Heisenberg models, to have a symmetry breaking transition below 2 dimensions, it can be generalized on complex graph, on an homogeneous structure, and the existence of a phase transition on a complex graph only depends on the value of the spectral dimension. And the result is exactly the same. So if the spectral dimension of a complex structure is lower than 2, a model with continuous symmetry cannot undergo a second order symmetry breaking phase transition on that graph. Okay? So this is a first result, I would say, that votes in favor of the spectral dimension being the correct tone control parameter for universality on non-homogeneous structure. Other things that have been checked is that solvable models like the spherical models, so models which are intrinsically Gaussian, even if with some constraint, the universal properties of these exactly solvable models are exactly determined only by the spectral dimension. So I take my exactly solvable model, I place it on a inhomogeneous structure which has no translational invariance. I can still solve it because it's quadratic. and I can show you that the critical exponents are only depend on the spectral dimension of the graph. Okay. The problem is that there is no example, or up to my knowledge, there is no example of critical exponents of an interacting model like the icing computed on a structure which has a finite spectral dimension that shows agreement with the numbers derived from continuous field theories. And so a lot of people, and I have been talking also with Meran Kardar, but you know, he's a big expert in critical phenomena. He believes that it's not true that there is a universality on non-homogeneous structure. And many people don't believe that because there are no evidence of that. And I believe one of the reasons there are no evidence for that is that there is no easy, or there is no simple lattice model inhomogeneous in which you can tune the spectral dimension. And this is what we wanted to generate for. So we wanted to give numerical, or even analytical if we can, proof that critical exponents on inhomogeneous structure with finite spectral dimension agree in interacting cases with the one provided by continuous field theory. But first of all, we have to make at least an example where we believe things behave relatively good. And what we did was to take a ring geometry, so a ring structure, a lattice in one dimension with a periodic boundary condition. We know that this has spectral dimension equal to 1. But then we add additional bond with a probability that depends on the distance between the site on that ring. Okay, it's very easy. So the probability, here it's a proportional, but it's actually equal. So depending on the distance between these two sites, and we can choose the chordal distance, or we can choose so whatever distance, but any kind of distance, meaningful distance on this one-dimensional ring, and we decide to add that link with a probability that's given by that. And so we find something which is obviously non-homogeneous, so you cannot solve any model that you put this by Fourier transform. But still, you can, for example, take the average. So this model will have different, given a fixed number of nodes or links, whatever. This model will be always different because it has a probability distribution, there is an extraction, a random process involved. But when you do the average, you find just a adjacency matrix, which is, so the adjacency matrix of this lattice is just 1 and 0. No? The bond is either on or off. But if I take the average, in the sense, if I take for each bond the probability that it's on, then it makes a weighted graph in which each bond has an intensity, and I can, at that point, translational invariance is restored, and I can make exact solution, so I can make exact computation on that graph. So, well, maybe before showing this, sorry, it would have been better if I put these slides before. So, sorry. Oh. Okay, my point is that if I solve that model, the average graph, so not any realization of the graph, but the average graph, the spectral dimension depends on the power law of decay of the probability that I have inserted. So this is what you have to take from this slide. I'm sorry that I didn't show before, but now talking, I realized that it's better to say it before. So I know that for the average graph, this is the spectral dimension of the problem because I can solve the average graph exactly, okay? And now I can go back. We will be there. So my point is, I have taken a lattice structure, I have had random bonds given by this probability, and now I can solve the average of the graph, which is a weighted graph, and I have shown you that the spectral dimension depends on how I make decay this probability. So this probability decay with the distance with a power law, and the power law is parameterized by a decay exponent sigma, which is a real number. Now the problem is, how does the actual model that I introduced, so not the one that's a weighted graph, the one that's just an adjacency matrix of 1 and 0 and that's randomness in it, how the spectral dimension behaves. But I expect this spectral dimension to also depend on sigma, because somehow I expect its properties to be somehow similar, if not identical, to the one of the weighted graph that's obtained as an average. Okay, we did this numerically. We did the spectra of this model at increasing sizes. We checked that the spectra are self-averaging, in the sense it doesn't matter if you make a lot of realization and you average the spectra between each other, or if you make a very big realization, the results converge to the same spectrum. And we have done this with different values of sigma. As you can see, for smaller sigma, as it may be expected if you think about it, because you have longer range connections, and so it means it's more and more difficult to reach the thermodynamic limit. There are larger finite size corrections. Anyway, we could get sense of this spectra. We analyzed the low energy tails. We made a lot of different analysis. It's complicated to fit spectra, but you can do something. We also calculated the return rate of random walks, which gives you somehow the same information, but it helps you to control numerical errors. We also tried with different definition of boundary conditions, so open and periodic. We also tried with different definition of the distance, so chordal or linear. Okay, we made all this work, it's numerical work, and we obtained this. So this is the spectral dimension of the model. In some sense, I was very puzzled by this result, because this model is random, it's true, so there is disorder involved, but there is no any kind of frustration or anything. It's just, there is no frustration in the model, but still, the result from the average graph diverges, or it's very different from the result of the, of the quench disorder. So I call it quench disorder when I make the average on the spectrum, and anneal disorder when I make the average on the graph and then compute the spectrum. So in principle, we were expecting the two results to be the same, and just not just because we are not very well at guessing our results, but even because there were papers in the literature that were claiming this, so that were claiming that the spectral dimension of the annealed model, so the one which is rotational invariant, and the one of the quench model, the one when you take the average on the spectrum rather than on the graph, were the same, but this is not the case. This surprised me. And so before even trying to simulate the Ising model on this graph, we found out that there is this correction to the spectral dimension of this problem. And okay, so as you see, at least here in the interesting range, so there are some numerical inconsistency between the green points are from the collapse of return probability of random walk, and the orange point are from the collapse of Laplacian spectra, of the spectra of the model. So here the numerics is not very trustable, but at least in the interesting range for ON models, prego.
So the deviation is for short range interactions, right?
No, the deviation is for long range interaction.
There is a deviation.
Here you see. Ah, no, you mean the deviation from the, yeah, sorry, yeah. The deviation is it's for short range interactions, which is somehow you may expect it if you're an expert in critical phenomena, because we know that critical phenomena can become trivial above 4 dimensions. It's strange because in this case, this order is not critical. So I didn't make any fine tuning at criticality here. Here, the density of states is power law for any choice of, so in principle, I can consider this. So I'm sorry, these slides, could have made them better, I understand, but.
Yeah, the slides are impressive, but just
yeah, but yeah, well, it's when you want to be impressive, but you are not. You are more focused on physics than being impressive. Let's say it in a positive way for me. So the point is, I can make it a critical model if I put, for example, a parameter here instead of one, no? I can make it a percolation model. So if I instead of a one, I have a C here, a parameter, I can move it, and the graph can be non-percolating, so can be a bunch of disconnected, or it can be a well-connected graph. So well-connected, a unique object. And this is a percolation, and we have studied the problem of percolation on this graph. This is how we get interested in this problem, because before we studied the percolation. But then we somehow realized that even if you put yourself well in the percolating regime, because when you put this parameter to one, the system is always percolating. Whatever realization you do, it will always percolating, because the backbone, this one-dimensional ring, it's always on. Because if you take a link of size 1, the probability to be on, it's 1. So the backbone is always on. Somehow, it always shows power law behavior in the density of states. This is not so surprising. But we were expecting this power law to be trivial. We were expecting this power law to be the same that you obtain for what we call the mean field model. So it's something which is very above the critical threshold of percolation. In a regime where there is no fine-tuning, there is no frustration in this model. So the disorder, yes, it's disorder, but it's not frustrated. It converges in the thermodynamic limit to a well-defined object without the need of averages. So for me, this result, it was puzzling. But then, for a moment, let me buy this perspective. Even if I am very far off the critical point of percolation. I'm in a well-percolating regime, and in principle, I have no reason to believe that there is any critical scaling involved here. But let me play this game for the sake of fun. I take two models, and I know because I've studied them, what I call a phi to the 4 long range. So in this case, there is no disorder involved. So if I take two models, which have long-range interactions, but no disorder. So this is a phi to the 4 in which the kinetic part, it's anomalous, it has some non-analytic powers. And if you try to make sense of this mathematically, it's a disaster. But since I am in continuous space with periodic boundary condition, I can take the Fourier transform, and it's a standard. So I don't need to deal with boundaries. If I had to deal with boundaries, it would be messy, but I don't have to deal with boundaries here. So this is what I call the long-range model, and this is what I call the short-range model, which is the standard phi to the 4 theory. I know that the critical exponent, or better say, the universal properties of the two models are somehow the same if I take the short-range model in an effective fractional dimension that's given by this formula. Okay, there is nothing exact here. It's a scaling argument, but it has been shown by myself, but also by other people, that it works quite well, okay? So I called it at one loop. Actually, if not a one loop, it's a little bit beyond one loop, but just to give you a flavor. It's not an exact relation, but it works fine. The universal properties of the long-range model with D and sigma fixed are the same one of a short-range model in an effective fractional dimension given by this formula. Now, I use this formula backwise to define the anomalous dimension of the long-range disorder. I do it, I just use it backwards. And so instead of obeying the mean field formula, now I found a correction, and I call this correction eta. And I compare this eta with the one of the Ising model found. I use functional G, but as I showed you, these numbers agree, whatever decent approximation you do. And I find that the two quantities, they correspond very well. And they also correspond well where the S is smaller than 2. So in a region where the people believe the universality does not even exist. And frankly, I don't have a justification for you. This is just what I noticed. So from numerics and by playing this game, I found that this model of disorder, which is, I repeat, non-critical, has an anomalous contribution to its spectrum as a form of a power law. And this anomalous contribution agrees with the anomalous dimension of the Ising model in continuous dimension. And I hope that somebody is interested and somebody can make some sense about this. I guess my time is running out, or it's already run out. So this was something not for you, so it was motivation. So I didn't skip because it's late, I just skipped because I guess it was not so interesting for you. I just wanted to acknowledge my collaborators, which are all the people in Heidelberg. So these two, she's not in Heidelberg, but, and so thank you. This is the archive reference. Thank you very much.
Yes, we have time for one quick question. Okay, so maybe we could better proceed. Thank you very much.
Thank you.